Hello, can everyone hear me? I'm sorry I look better in the picture that they had on the screen before than I do in real life, but I'm sure you'll make do. Anyway, imagine this. It's 9 a.m. on a Saturday, and you've just packed your car for a weekend away from the computer, away from your home. But all of a sudden, your pager starts beeping. It's an incident in production. You reluctantly open your laptop to see what's going on, and you start off with the standard diagnostic things. You go and look at your infrastructure metrics, but everything is green. None of your servers are using too much CPU. Nothing is run out of memory. So you jump forward and you have a look at your application traffic. And here again, it looks pretty normal. The lines aren't going up dramatically to the right or dramatically down to the right. As an industry, we generally think this is pretty good. So you crack open your system's architecture diagram to remind you what this checkout system actually looks like, how it's built, where else you might be finding issues. And you were immediately confronted by the incredible incidental complexity of this thing that you've built. For something that's seemingly quite simple, a checkout system, a system for taking orders on a website, there are lots of different components in play, and there's a lot to hold in your head to work on the system. So you dive through your diagnostic dashboards a bit more, you convince yourself the infrastructure is more or less working, and you jump over into your application traces to see if you can find any requests that are failing. And it jumps straight out at you. It's an actual exception in code. It's not something to do with server scaling or Lambda. It's just a good old-fashioned issue. So you open your ID of choice, which should probably be IntelliJ, I think, these days, and you get to work starting to fix the issue. And you're immediately frustrated when you realize that this seemingly simple fix, this thing that looked very simple from the exception in the logs, is actually very complex to fix and cuts across an enormous portion of the code base, as we can see from this heavily commented GitHub issue here. And you sigh as you realize that the system that you've been working on for 4 or 5 years now, it's no longer this beautiful greenfields project you started with. It's become this incredible, complicated mess, and it takes longer and longer to make what used to be seemingly simple changes to it. You think back to the day that you founded the project and you say, hey, is there something we could have done at the start to avoid this misery down the road, to try and have maintained a higher quality bar for our code base for much longer going into the future? Hi, I'm Scott. I work at Datadog, and I'm here to talk to you today about building quality software so that we can build quality software that we can actually keep using for many years into the future rather than just throwing it out and starting again over and over again. And there's lots of stuff these days to distract us from this goal as an industry, lots of things that you would probably call incidental complexity. Rather than focusing on building our code, we can decide to explode it into microservices and scatter it about the network. And while I think this is a fun pastime, I certainly have a lot of unnecessarily complex things running on my Kubernetes home lab at home. I don't think how we decompose our systems really affects the tooling or the fundamental need for managing the quality of the software itself. It's just something else to distract us from it. Likewise, the cloud. This is another giant box of fun tools and things that we can prod and combine together in increasingly intricate ways with one another, like we saw in the very serverless architecture diagram I showed before. But again here, I think where we deploy our code is largely orthogonal to how we manage the quality of that. And another thing that has made this quest for quality maintenance a bit more relevant these days, I would say, is certain modern tools like generative AI, which produce code like this, which I kind of want to share it because I think it's really funny. On the one hand, it's shocking, like in Rust, if you haven't used it before, it's very easy to generate a random number. But at least in this case, Claude Code has put a nice comment on the top that says, this is awful and I shouldn't have done it. So, there's a bit of self-reflection there. Anyway, we don't want stuff like this in our code base. And ultimately, with all this stuff, with all these things to distract us from working on our code itself, one fact remains, and that is this idea of shift left. The earlier that we can catch defects, the cheaper they are to fix. If we can catch them before we write code, that's the best. If we can catch them before they get through a PR request, this is also very good. Anything we can do to shift things left reduces the cost of those issues over time. So if we go back to this hypothetical scenario that's interrupted our weekend and have a bit of a think about it, the code base is a big mess now, right? It's been going for ages. We don't like touching it anymore. And there's kind of this inherent developer desire to throw it all away and start again so we can return to the glory days of greenfields. But I think as an industry, we've kind of realized this often doesn't really help, right? We spend a year or so, maybe good case, rebuilding the thing, and then we end up with new problems at the end that are different to the old problems, but it's not a panacea, essentially. But if we could go back to the start of this hypothetical project and start again, what sort of things could we put in place to try and avoid the misery down the road? And what we're really talking about here, and the word I keep saying, is quality, which brings me to this quote that I am rather fond of from a gentleman who wrote a book that's notionally about maintaining motorcycles. Quality, you know what it is, but you don't know what it is. And the takeaway here is that it's not a word that really has inherent meaning devoid of a concrete domain. You don't just point at a thing and say that's quality, and why that thing is quality is inherent in quality. It depends on what the thing you're pointing at is and what you are searching for. And what I think that we're chasing as software engineers and people building software systems when we say quality is actually longevity and maintainability. We want to build systems that we can continue to maintain well into the future confidently without worrying that we're going to introduce exciting classes of bugs because it's no longer possible to understand the system at the end of the day, or without having to spend innumerable hours to do simple changes, like in this hypothetical example I had before. So if you ask software developers, like, what can we do to make sure our systems last for ages and are great? I think most people will kind of say, yeah, well, we just think really hard at the start. We do design. We do some UML maybe if we're a little bit older like I am. We think very hard up front in kind of a waterfall fashion, and we try and stay on the rails with the design over time. And I think this is certainly important. I think if you start a system, if you go to Claude Code or Cursor or whatever and say, build me a checkout system and just let it do its thing, and you don't think at all about the framework in which you want that to work, it might work briefly, but it's certainly not going to be a system with much longevity. So I think it's worth reflecting on the design of the system up front, surely. But I also think here it's not a panacea. And the reason for that is over time, requirements diverge from reality. You have new requirements, they force you to build the system in a way that your original architecture, your original design did not consider. And this can diverge in a way where you actively notice that you've diverged from the design. You say, oh, hey, this design is no longer appropriate, and maybe you go and update some static design documentation somewhere. Or it can diverge in a way where you don't even notice that you've gone off the rails, and you end up with all these little consistencies. And when we talk about technical debt, these are the sort of inconsistencies that slow you down and start to cause the introduction of issues over time. One class of tools that we can use to help with this, to kind of shift left and start to encode quality checks into our pipelines, is static analysis. And this is going to be kind of the first part of the talk I want to focus on. And to start off with, we'll look at linting and style checking. And I think this is super boring, right? Like, I don't think anyone's too excited about this, but I also think it's fairly foundational when you're talking about the quality regime for a programming language. Code style in particular is something that used to really irk people because somebody would come in and they would go and turn on something like check style. Who in here uses Java, by the way? Sweet. Who here hates check style? Well, mainly maybe me. So I'm sorry about my opinions, which might not align with everyone else's. But you often have tools that enforce a style guideline that's really finicky, and you can't easily reconcile your code base with that. And then people get a bit sulky about having to use the tools, and that's fair. If they add a lot of friction, if they slow you down, that's not great. I think the state of the art for these things is much better these days. And ultimately, although it's just aesthetic, I think anything you can do to reduce the cognitive load when you work on a code base, so when you look at the code, you don't have to think as hard about what it means because it all looks roughly the same, pays off for itself over time. Linting is an even easier sell. Here we're basically just trying to find statically common patterns of bugs in our code base so that we can automatically prevent them from ever getting in. There's a bunch of different tools we can use for this. They're rather programming language specific, although Sonar is a really cool one that cuts across most languages and gives you a lot of other shiny features. But I think the pragmatic advice here is really just use what the industry is using or your company is using for the technology you're embracing. And for the formatting side of things, I think it's very easy to find these tools that can lint your formatting but can't fix it. The trick is to just use something opinionated that applies like the Google style guide to your Java, for instance, like Spotless does. And not something that has lots of different tunables, so you can have all these meta arguments in your pull request where somebody says, yeah, I broke the formatting, but I also updated the formatting guide so it matches what I think is right. I think that's rubbish. I think there's no absolute truism with code style. I think the trick is just to have local consistency. So with those two comments, I would like to show you all a bit of a sample application that I have prepared today. And this is kind of like a semi-serious thing. If you can see the back of my laptop, I've got a pile of Datadog stickers. I work for Datadog. We have merch stickers like everybody else. And me and some of the other folks in the company are building a fancy microservice thing for collecting these and sharing them with other people. It's all very serious, important business stuff, as I'm sure you understand. This here is the sticker catalog service. So it's responsible for storing the stickers themselves, constraining the supply of them, and both the metadata and the images. It's pretty straightforward. And when I work on software projects, I like to have a README that really tells you everything you need to work on them and understand their purpose and understand how they're structured, more or less. So here we can see straight off the back that we're using Quarkus, we're in Java world, and immediately kind of the high-level technology decisions. We're using Panache for data access, we're using SmallRye for messaging, OTel for telemetry. We can see the main API endpoint. And as we go down, we have kind of a high-level view of the architecture. So how we've broken down the different domains within the project, how the shared packages are structured, how we fall through in terms of our model structure and our layering, which are things that we used to care a lot more about with enterprise Java. I think it went a bit extreme there for a while, but it's good still, I think, to lay down kind of a reasonably high-level architecture in this fashion. So anyone contributing to the project can immediately jump in and understand roughly how their contributions fit into the overall structure of it. Something else I'm super fond of these days is that you can embed Mermaid.js into pretty much any Markdown editor. So here, it's nicely rendering this layering diagram of how the project's structured, and it'll do that in GitHub as well. So this kind of like old thing where you'd use a tool like Enterprise Architect and build this big fancy architectural model that no one ever looked at. Although this isn't something that's being automatically tested against the code base CI/CD style, which I'll come to later, it's still versioned with the code and it's still very low friction to update it. So there's no longer this excuse like, yeah, I diverged from the design and I would have updated, but it's too hard. You can do it all in the same commit. You can say, hey, I needed to change this because the design has been pushed out by new requirements. You can make that change. So once we have a bit of a look at that, I'll show you quickly how I'm doing static analysis stuff in here. And like I mentioned before, it's nice to have a formatter that just works. It doesn't give you lots of tunables, that gives you nice formatted code and a way to check if it's formatted. Spotless for Java is great for that. You have very few tunables. You say, I want the Google Java format, which I think is pretty inoffensive. I don't want unused imports. Apply it to everything. You have two targets. You can check it. Like, is my code well formatted, which is what you would run in your CI. And you have apply, which makes it formatted if it is not. Simple. And with this target here, you can just add this to your Git hooks, right? So there's no longer any excuse for, yeah, the formatting check fails in CI, but it's too hard to fix the formatting. It's so trivial to do that everyone can just be consistent from the start, and we don't talk about it anymore. Likewise, for linting, I'm using error-prone here. So because I don't want to have my build broken all the time, I have this class off to the side, which is named, oh, I don't know how to deal with that. I'm using presenting mode and I don't know how to close the left tab. Does anyone know? Well, this isn't bad. Sorry?
Split in.
Unsplit.
Sure, last.
Command-Shift-A. Unsplit. This was an intentional part of comic relief in my presentation, in case anyone was wondering. Cool. So thank you for that. I learned something today. So here is a class that I've written, which is called the unfortunate event recorder, because it is rather unfortunate in the way it's written. And to make things simple, I've inlined a bunch of the error-prone lints here so we can kind of see the sort of stuff this would pick up. And some of these are super interesting, I think. Like this one here, if you were reviewing this code, I'd say 9 times out of 10, you would probably notice that this is never going to return true because that's a byte, which doesn't go above 127. The trick with linting is that a lot of the things it picks up are often really inane and kind of obvious, but if you rely only on the due diligence of your pull request reviewers, of your programmers to pick up these simple things, then at some point these bugs are going to creep in. And they're so obvious that that shouldn't really be the case. By using basic linters to pick these things up, they can just never get in. This one here is kind of like the classic new programmer thing, I would say, where you think that what I call rather incorrectly the hat operator is used for an exponent, like to raise something to the power of, but it's really a bitwise XOR. And for this, we've got kind of 2 errors coming back, like a number XORed with itself is probably not a thing you want to do. And this here looks like you're trying to raise it to a power, but by the way, that's not what happens. And I think this is great because I still remember discovering that this did something totally different. I think most people go through this. Again, it's super obvious generally, but by embedding it into a linter, you don't have to worry about it. We have a bit of more serious ones down here. This one here is telling us that using uppercase Y, which is week year in a date pattern without week and year, is probably wrong. And it's kind of insidious because I personally would never notice this. I don't spend enough time thinking about the nuances of Java date formatting to recognize that difference. And it's still valid. So it requires a lot to go well to realize that this is wrong. And in this case, we're just being told automatically, don't do it. And finally, here we have one where we have an open character class and a regular expression, which is visually rather traumatizing to look at, to be honest, but we can automatically get it out this way without having to think about it. Cool. Let me return to my slideshow. So we've talked about kind of the foundations, the foundational things in static analysis that we start to look at for quality control. Another aspect of quality these days, and something that, I mean, it's always been there, right? We've always cared about security as an industry, but it's become much more important more recently is security. And security is another aspect of quality, I would say, the same as making sure you don't have other regular classes of bugs in your code base. So we imagine that Jane in security keeps telling us to fix the log for shells. We haven't touched the code base in years, and we have no idea what she's talking about anyway. And there's been a lot of this sort of issues lately, both accidentally broken but very high impact ones like log for shell, and intentional supply chain compromises. This has become something that we as developers need to handle as a normal concern within our software development lifecycle. The tools that we use for these particular ones where something in our supply chain is broken are called software composition analysis. And they do exactly that. They dig through your entire dependency tree, they correlate those versions back to a CVE database, and they say, hey, this thing here you're using is out of date, in this case, from Dependabot on GitHub. Or this thing here is out of date and also terribly compromised in the case of this crypto dependency I should probably fix in my parse API. And Dependabot is great here. It's something that lots of people are just using by default because most people are using GitHub for everything these days, for better or worse. It gives you really good results out of the box. And in many cases, it'll just cut a PR for you and you can merge it when the build doesn't fail and be happy. And there's lots of other tools you can use in this space to go further as well. And they always kind of have a separate angle that is often of extra value. Who here uses SonarQube, by the way? That's great. I love SonarQube. I'm really pleased to see that it's still super widespread. It's quite cool. They do SCA as well as application security testing that I'll come to in a minute for you. And their big thing from my perspective is that they have very good quality control dashboards as well. So you can track all of the key quality metrics for your code over time. You can gatekeep your PRs against them. Your linting count must go down over time. Your coverage has to go up, all that sort of stuff. At Datadog, the kind of extra thing we do is overlaying runtime information on SCA. So we can say, hey, this library version you have is compromised in your code base. By the way, it's running in prod at the moment on these pods, and there's an active exploit available for it. So maybe prioritize that. In practice, this is super useful because if you're listening to me now and you're saying, oh yeah, we should probably do that, and we're not yet, and you have a big existing code base and you go and turn on all the SCA things, you're going to get so many errors coming back and it's going to be super overwhelming and you're not going to know where to start. If you have some insight into what is actually currently compromisable and running in your infrastructure rather than just the static code, it helps you focus that down a little bit more. But really the big insight for this section is like it's worth doing. This is kind of table stakes for quality management these days. Dependabot is great, a great way to get started. And if you're in the other lifecycle, in the other tools already, like SonarQube, everyone is, check it out. And within the class of quality issues that touches security, we also have ones where we have actually written our code in a way that is compromised. So not just somebody in a downstream library has done it, we have done it ourselves. And what we want here is application security testing. So we can address issues like this. I want to make sure that Joe the intern is automatically preventing passing unescaped user input to raw SQL queries. And this isn't a dig at Joe. Like I've been Joe before. I think everyone has a bit of Joe in them. And you can imagine that more often than not, if you were changing an existing system to get something like this, you're not writing the whole flow. Like you're going and adding a new endpoint somewhere that uses an existing database call in the back, and that lines everything up so suddenly you have this SQL injection in there. So even here, the due diligence of your PR reviewer isn't helping you because they look at this little slice of things on top. If they're really attentive, maybe they'll check it out and have a look as well. But it's very easy for these sort of errors to creep into a code base if you don't have a way of automatically preventing them. And as I say here, this is where we're talking about application security testing. We have tools like semgrep and CodeQL that we can use for this commonly, as well as SNCC. And these are both tools for finding security issues in your code bases. Sorry about that. As well as general purpose tools for asking questions of your code base. So you can go and compile a model of how your code works, how data flows through the different paths in the code, which is what you need to know to say, hey, unsecure input here ends up over here, as well as how the types and everything relates to each other. I think this is super cool because you can go and write arbitrary queries or scripts that ask questions of your code to check things. You can use it to write architectural assertions, for instance. You can use it to say, print me all the API endpoints I have, all sorts of things like that. But you can also generally, concretely with both of these tools, run an application security testing suite that has a bunch of opinionated tests in it already. So if you use Java, for instance, and you use CodeQL, you go and say, hey, run the Java security and linting test over this. And with its understanding of the common libraries in the Java ecosystem, it goes and hunts around for all these patterns that lead to SQL injection, other security issues for you, without you having to write queries. CodeQL is a good one. It's a GitHub tool. You can run it both very easily from within GitHub. So you can go into GitHub itself. You can go through their workflow builder and say, please give me a CodeQL. Thank you very much. It's not like Dependabot. It's actually going to go and configure itself a build job in your repository for you. So it consumes build units and whatnot, but it sets everything up. And I find GitHub workflows very tedious to work with. So this is cool. If you're not doing anything for this already, it's something where you can get started really, really quickly, and it'll go and look at your project and say, hey, I need to set up the .NET stuff, the Java stuff, the Python stuff. Here are the default rule sets to find security issues. Annotate my PRs for me, please. What I find more interesting, I mean, the SAS stuff is very important, and we should all do it, is that you can use these as general purpose query runners, because this is a whole world of interesting metaprogramming where you can start asking questions of your code base, and I think it's very nerdy and entertaining. And in the CodeQL side of things, this is how that works. And I've omitted a little bit here, so it kind of still fits on a slide without being too small. But the gist of it in this case is that we have a source and a sink, and at the bottom we say, please give me all of the paths between the source and the sink. And again, this is a query running against your code base, right? So the source is anywhere in the code base where we construct a string literal, like you put a string in a quotes or you go new string, anywhere. And the sink, which I've omitted, would be the construction of a URL, which is a bit more long-winded, but still rather understandable. And what's interesting with this is that it's not just going to give you instances where you go new URL localhost or new URL cool server or whatnot. It finds instances where the data flows through the whole graph of your program and ends up in the URL. So you can imagine that you go and implement a configuration management framework and you DI that into somewhere else. And you just write in the get value function, return to do as a string literal. This would find that. This would find all instances of that. And this is a bit of a contrived example to find things like that, but this is exactly the pattern you need to do to find things like SQL injection, say, where the sink is anything that constructs a raw query, say in Java with Hibernate, and the source is any unescaped user input through your JPA API endpoints. semgrep is similar. It does similar things. It's much simpler. You write the part in here that's the query is the pattern. The pattern looks exactly like the code. So you say, find me all instances of using logger info and capture the data. You can run semgrep just as a CLI without having to create a YAML file. So you can just go and write ad hoc queries to ask things about your code base, which I think is super useful in some cases. But it does all the same sort of stuff as CodeQL. Concrete recommendations here in terms of quality are, we kind of all need to do it. It's the same as SCA. I think mostly, or in many cases, you already have tools around to do it, like SonarQube, just be a matter of turning them on. If you don't, again, the GitHub default tooling is very good. And on the code query front, it's a fun pastime. I hope I've kind of conveyed that to you. There's lots of interesting things you can do when you start to think of your code base as a queryable artifact. Some of that can be used to support assertions that you care about maintaining, like architectural style, which I'll come to in a minute. And other things are just useful for discovering foreign code bases, I find. And that brings me to my next point, which is architecture and kind of how can we automatically maintain architecture over time. So we saw before in this sample application, I have this README. I've gone to great lengths to write down some Mermaid.js diagrams, to write some documents about how I want my project to be structured. It's easy to update that because I can just go through and I can edit it when I do my PRs, so there's less excuse than using a big old enterprise modeling tool like we used to do. But still, it will diverge from reality over time for various reasons. So wouldn't it be great if we could automatically test that, if we could have rules that we write down, like a regular unit test, to enforce our mental model, our architectural model of the code base over time. So when it diverges, we either address it by updating our model of the architecture because it needs to be updated, or redressing our changes because the changes we have made are accidentally bad and we've not realized them. And unsurprisingly, this is called architecture testing. And there's a couple of different tools to do it. There's not as much in this space as I'd kind of hope. For Java, we're quite blessed with ArchUnit, which is really very good, and I'll show you a little bit of this in a minute. Sonar have recently come out with architecture as code, and when I say recently, I think I mean the start of this year, last year. Their approach is a little bit different. You write a YAML document, you version it with your code, and Sonar Cloud comes in and assesses it against it. I haven't played with it yet, but it seems quite promising, and it's cool to see that it's spreading a bit beyond ArchUnit. .NET also has ArchUnit.NET. Anyway, you can do things like this. And these are pretty much reflecting what we saw written down in my README before. We care about things like layering, that if you have a resource that represents your API endpoints, it's not using your persistence library directly. You have indirection through that. We care about naming things DTO if they're in packages called DTO. We care about things that implement interfaces having consistent names, at least in Java. And we care about packages over here and packages over there not being mutually dependent on each other, which is something that comes up quite a bit in Java. And in ArchUnit, this is what those rules look like. And it's super readable. Like, this is a regular JUnit test. We don't have to do any weird compile time magic or Maven hackery. This just works out of the box. No classes that reside in a package sticker should depend on classes that reside in a package award because domains should be isolated. You can run that as a normal test. It's super clear what the intent of it is. And if you break this rule when you're developing, you are flagged just like any other unit testing. So I think, does anyone do this already, by the way? Like, how popular is ArchUnit? This is super interesting because I asked this at a Java user group a couple of weeks ago, and about half of the group put their hands up, and then I was like, oh, why have I mentioned this? Everyone already knows, but it seems less popular here. So cool. Great, let's have a bit of a look at what that looks like concretely. Let me quickly jump over here. Cool. So I have a bunch of different tests in here that basically reflect the will of the README back into unit tests. And this first class is technology governance. Can everyone read that at the back just to make sure sweet. And basically the idea of the tests in here is that in Java, in particular, there are 1 million ways to skin every particular cat. And even though I'm using Quarkus here, and it's quite an opinionated batteries included framework, you still end up with, say, for logging, 20 different variants of logging facades just out of a default Quarkus application. And you really only want to use one. So in here, we're saying, hey, let's not allow people to use SLF for J. Let's not use log for J. Let's not use Java util logging. These are all in the class path of this fairly minimal application by default. We only want to use JBoss logging. We can run that as a regular test. Everything does exactly what we want. It is very easy for us to ensure consistency here and thus maintain the quality on this little axis of the project more effectively over time. Likewise, I would like to use Panache, which is an abstraction over Hibernate to make it a bit easier to work with the ORM. Hibernate is still there, but we shouldn't be working with it directly. So here we say, hey, if you have accidentally gone and started using Hibernate or intentionally or whatnot, that's a no-go. Go and use the Panache abstractions. This one is interesting because when I wrote this test for this talk, I ran it and it failed because I had accidentally used Hibernate. And I was like, yes, I'm on the right path with this. So there's a few more of those. Kind of the classic Java one is caring a lot about layering. So here we're saying, if you're in the REST API, you should not be depending directly on entities. This is super uncontroversial in most projects. We're identifying the REST APIs by saying names that end with resource, and we're identifying entities as things that reside in a package entity. And we get a nice error back if we do it, which tells us exactly what we need to fix, right? This is the same sort of thing. Resources can't use repositories. The kind of last one that is interesting, I would say, is domain structure tests. So here we have, just pop the sidebar up for a second. We have the notion of these different bounded contexts within the application. So you could have a domain for a sticker catalog, say. You could have a domain for unfortunate, which is unfortunate. But each one of these should have kind of a consistent structure to it. It should have DTO, entity, event, things, and these should be named in a particular way. We want this pattern to continue ad infinitum between our different domains. So when we work on the project, it all looks the same. It's all consistent. There's less potential to accidentally introduce errors. And this gives us that. We're basically saying, hey, DTOs should all be named DTO. They should be in DTO packages. Events should be named event. They should be in event packages. Basically, enforcing all of those things that are kind of structurally visible when the project is simple, but are very easy to incrementally diverge from over time. And the last thing I will show you really quickly here while we're here, and this is jumping back a little bit to CodeQL, is how CodeQL works when you use it as a query engine. So it's an interesting one in the sense that you have to create a database separate to your application's code to actually use it. So basically what's happening is you're running a Maven build, and within that CodeQL is instrumenting it and discovering all of the metadata it needs to build up its flow graphs. And then we can run queries about it. So in this case, we're saying analyze it with the Java security and quality pack, which is kind of the default, find me application security testing quality issues in this code base, please. Check. You get a big long CS feedback, so I'll kind of skip showing you that. But here are a couple of examples of things that come out of this. And this one is interesting in the sense that this is a very simple application, right? Like I haven't written heaps of code to end up with security issues in it, but I also haven't intentionally put security issues in it. And this is one. This is it saying, hey, in this instance where you're calling this logging function with ID, that is user provide input that you have not validated for things that shouldn't be in there. Probably you don't want to do that. This is true, like I should go through and fix this. It also comes back with a bunch of generic linting errors. In this case, this is kind of interesting because error prone didn't pick it up. It's just saying maybe you don't actually want to use get resources stream here. I think I do, so I'd go and mark this one as ignore. But it's interesting to note that CodeQL is also able to pick up these sort of things for us. Cool. Let me jump back over here. Great. So spent a bunch of time, 33 minutes in fact, talking about static analysis. One other kind of obvious class of tools, if we're talking about maintaining quality, is dynamic analysis. And this is stuff like unit testing, right? The architecture testing that I showed you before, this is interesting because although with Arch Unit, you were writing it in a unit test, the unit test is really doing static analysis for you. Like you could also write an architecture test as just a YAML file describing your architecture, right? So although I think the mechanism for executing it is dynamic, it's actually kind of a static testing thing. But anyway, it's also stuff like micro-benchmarking, fuzz testing, all these sort of things. And everyone's doing unit testing these days, right? Like it's table stakes for software development. But something that I think is actually rather important and often overlooked for software quality management these days is observability. Perhaps unsurprising for somebody from Datadog, but like also I think rather true. And the reason for this is simple. Like we can have all these beautiful architecture diagrams of our system. We can have discussions about how it works. We can have pull requests and code quality and shift left things and all of this. But if we don't actually look at how the thing is running, how it's performing, what our error rates are, if we're regressing the performance of it over time, have we done good? Do we know that we've done good? If a code quality tree falls in a forest and no one's there, was the tree good quality in the first place? This is a bad joke, but I think that you know where I'm going with this. And observability these days is primarily three signals. We have logs, which I think everyone knows what they are because we tend to encourage people to do 12-factor application development these days. We want JSON records to standard output, so you have a field for the message, a field for the level. You can pass meaning out of it very easily. Metrics, which are numbers about the system over time. How many requests per second are passing through this load balancer? What's my error rate? How much CPU is this one particular pod using here? And because we are all enthusiastic software people, we have tracing, which is what I think is the most useful one from kind of an application developer perspective. Tracing lets us grab any particular request through our system, that's been sampled and see how it flows across the system. So both within individual components of services and also across multiple components of the service, of the system, of a microservice architecture rather. So, and here's kind of a concrete example of that. Who's doing distributed tracing at the moment, by the way? Not many, so I think I'm on a good path with this one as well. This is Datadog. It doesn't matter, like all distributed tracing systems have a UI that looks very similar to this and presents similar data. It's just kind of the tool I have at hand. And what we can see here is one very concrete request through our sticker award service at 14, 23, and 48 seconds on the 26th of August. So it's a concrete request. It's not an abstract thing. This is something we've captured, passing multiple components in a microservice architecture. And at the top, we can see it all fires off in the sticker award service when it gets a message on the Kafka topic user registered v1. It immediately calls the sticker catalog service over HTTP, which is another service. Within the sticker catalog, it makes a query to its database. It takes 505 nanoseconds. That all returns successfully back to the sticker award service. It makes 2 queries to its own database, and then it writes a message off to another Kafka topic, sticker assigned to user, which takes 102 milliseconds. The whole thing is successful, completes in 107 milliseconds. And this is cool, right? Like you can immediately see that this tells you a lot about how your application is actually behaving. And it also makes it really easy to work out what's happened when things go wrong. So here we can see a sampled request that's failed. We can see at the top on the pass summary that we've got a 500. For those of us who are running things in prod, we probably realized the user who saw this got a message that said something has gone wrong and isn't super actionable. So without tracing, you'd probably go and dive into your logs and be like, is there a stack thrown somewhere here that I can decode? Do I have some errors, something useful? Lots of the time there will be, some of the time there won't be. In this case, we can see, diving through these kind of intermediate samples that we've got that have been added by Quarkus's instrumentation, the root cause at the very bottom is very clear: connection refused to the pass API. And all we've had to do to get this back from a sampled error is basically have tracing. Like we haven't had to actively go in and say, I want to capture the connection to this thing. We just shakes out. It makes it very easy to diagnose concrete errors, concrete qualitative errors like this, as well as performance regressions. And if we want to use distributed tracing today, there's kind of 2 things or 2 big decisions you have to make. The first is whether or not you want to automatically instrument your code, and the second is how you want to collect. In many cases, you don't have to change your code to get traces out of it. This is almost certainly not readable at the back, I apologize, but the main thing here is that we're launching a normal Java application at the top, and we're launching it with a Java agent, which is instrumenting it for us. So we've compiled the application normally, we've added nothing new to it. We're just saying, hey, use this Java agent. It's a Datadog one. There's also OpenTelemetry ones for a vendor agnostic option. And when the application launches, it has an internal model of all the different dependency libraries that can make external calls in the Javaverse. Like, you would typically use Netty for HTTP, or you would use Panache, say, for SQL queries. And in the Java case, it's using code weaving to go in when the application launches and wrap all of those downstream callers in code that captures those calls, adds tracing headers to it when it's HTTP so we can propagate the trace to downstream services, and overall build this big trace graph I showed you before without having to change any of your code. This is great. It works really well for languages that have a runtime where we can do this sort of manipulation of the application at startup time, which is pretty much Java, .NET, Node.js, Golang to an extent with a bit more trickery. Things like Rust and so on, you can't do this. When it works, in some cases, you don't even need to launch the application. If you're using Java, you can go and use, for instance, the OpenTelemetry collector in your Kubernetes cluster and say, hey, can you automatically instrument all pods that start? And what it does is when the pods launch, it adds some init containers, it injects itself into there and it goes, hey, this is a Java application. Do this when it starts. And that way you don't even need to change your container images, which is super cool. You can also manually instrument things. So you might say, hey, I like my containers to work the same locally as in production. I don't like this weird witchcraft that Scott is describing to me, which I think is fair. And you can go and add, typically these days, the OpenTelemetry API to the application to actually actively record what you want to capture. In this case, we're saying, hey, I would like to capture a subspan, so one of those subbars we saw in the tracing graph. For every call to grant award, I want you to capture the user ID as an attribute and a couple of other things here. And we can set all this up without auto instrumentation and then explicitly push this trace data off somewhere else. If we do this within an application that has been auto instrumented, this will get magically pulled up and used to enrich the auto instrumented spans. And that's kind of a sweet spot, because if you do it only the code way, you also need to go and configure tracing for all of the downstream libraries you use. So you have to go say, hey, I'm opening a connection with Hibernate, wrap it in the tracer for Hibernate. Or hey, I'm opening a HTTP connection, wrap it with a HTTP tracer. The kind of sweet spot that I found is to use auto instrumentation on the outside where you can, and then use the OpenTelemetry explicit span creation inside for things you care about. And then you get everything magically configured where it can be magically configured, plus a vendor agnostic creation of spans for things that you care about. So the application doesn't couple against a particular vendor, and you get the best of both worlds, essentially. If you don't want to use auto instrumentation at all, you can also configure the OpenTelemetry SDK, which is an extra component of OpenTelemetry that's totally disconnected from the API, but implements the API. So you can go and add this into your code base for whichever language that OpenTelemetry supports that you use, which is pretty much all languages. And you're really configuring it as a regular client. Then you're saying, hey, for all the calls through the tracing infrastructure that we've set up that produce tracing data, push them off to this endpoint over here, push them to Jaeger, push them to Dynatrace, Azure, whatever. Do that for me. And in that way, when you do it in this fashion, you have control of the whole thing. Your application is totally self-contained and behaves pretty normally. The way I tend to do things is using the OpenTelemetry API to describe what to capture, and using auto instrumentation when I can, because it's less to set up, but it's pretty low friction when you do it all in process as well. And with all of this extra information that we collect, we can really feed that back into our developer cycle. For a lot of these things, we can even encode these checks into our promotion through environments, right? We can say, hey, we roll this out and we regress the error rate for this endpoint so it's not going to prod. So we can use the actual data of the running system from this mechanism to prevent the promotion into environments. It's not as good, obviously, as having it really early on before a PR, before the code is even accepted into the code base, but it is still something that prevents it going further right. And the last thing I would like to talk about is that I lied before. The observability is kind of 4 things now. Continuous profiling is something that's becoming kind of interesting these days, something that I'm personally super interested in. And it's not just like a weird vendor-specific thing. This is something that's also being standardized in OpenTelemetry at the moment in a special interest group. And the big idea is this. Manual profiling is something that we have done for a long time to identify performance issues in code bases. And it's kind of a pain, right? Like, you can imagine that somebody's using your web system in production. You have a customer. And they come to you and they say, hey, I was in Porto on Tuesday and the sun was shining and I was looking west and there was a gentle wind and I pushed the checkout button and it was kind of slow, and I think it had to do with the surrounding environmental conditions, you know? Like, they give you some very specific and obscure description of something that happened and then say it was kind of slow. And your job as a developer is to kind of take this and be like, yeah, that's plausible, I guess, and translate it into something that you can actually profile on your machine. Like, I will reproduce a test case that I think will exhibit this performance issue that I notionally believe in here. And I'll run it on my local machine, try and reproduce that, look at the flame graphs that come out, try and fix it, push it through to prod, and then ask them if next time they're in Porto on Tuesday and the sun is shining just right, if the checkout's a bit faster. And there's a bunch of problems with this, right? Like, the first one is kind of obvious. It's very indirect from the issue. You're not doing this in response to measured production behavior. You're doing this in response to user feedback, probably proxied through some other parts of your organization. And the other issue is that the tools that you use to do this profiling historically have enormous cost impact on the execution time of your program. So when you use things like valgrind, gprof, they're going through and they are rewriting all of the calls in your program so that whenever they're made, they're recorded. Like, you hit this function, go off to the side, write down that this function was called and here was the stack. And that adds incredible cost overhead to the whole thing, which means that you're never going to do it in production, right? Because you can diagnose performance issues at the cost of making everything dramatically slower. What we've kind of worked out more recently from things like Java Flight Recorder is that you don't actually need to capture everything for profiling to be useful. What if, instead of capturing every function call, we just snapshot the state of the stacks in our application for every thread at some fixed cadence. So say 20 milliseconds, let's go and dump all of the stacks in our threads, put them off to the side. If we do this enough, we can infer where our program is spending time just by aggregating that view of all of the thread stacks. If something is wasting a lot of time, it will always appear. We will miss calls that don't spend much time. We have functions that are very little and very frequently run, but are very quick. We won't see those all the time. But this isn't really a problem because it means we're not spending much time on them. So it's a pretty acceptable trade-off. JFR is great. It makes it really easy to get this data in Java applications, but it's not a complete solution. It's something that you can run and you can kind of pull the data out of running Java instances, but there's lots of plumbing involved. The idea of continuous profiling is to kind of democratize this in the same way that tracing is democratized. We should be able to do this super trivially in production all the time. And I don't just mean this hypothetically, like you can actually run this in production. We run this in production on Datadog on itself, so you can go in and see the profiles of all of our prod services, and it leads to a bunch of people in the engineering channels being like, hey, I saw this was kind of slow, so I changed this one line and I saved this many vCPUs and this much money. And it's sometimes super dramatic. So you can get to a position where you can really use this to inform your development cycle, really use this to keep a handle on the quality of the performance of your system. And the other cool thing is, because these tools tend to be very tightly integrated with our tracing infrastructure, we can correlate the profiles we get back with the actual metadata of our running system. And this gets us to something like this. Again, this is Datadog. This isn't as common as the tracing stuff yet, but you can also do it with other providers, but just to kind of have a UI of what you see. We can see at the top here that we are diffing the profile from the product recommendation service between two different versions. So on the left, we can see a flame graph for one version. On the right, we can see a flame graph for the other. And we can see it's faster. We can see halfway down that we've filtered down to only profiles that are for the heavy computation option. So here we can really particularly say like, hey, I released this new version. I think I improved the performance for heavy computation. Did I? The answer is yes. Under production traffic, it is faster. It's this much faster. You can dive through the flame graph to work that out. And again here, because we have this data, because we're collecting it continuously in production, we can feed this back into our promotion process of an environment, through environments, to gatekeep things and say, hey, performance regressions beyond this point, no go back and fix it. Here are some profiles that show you what you've done wrong. So kind of the advice here is that this is the continuous profiling. It's like much newer. It's much less common than distributed tracing, but it's something that a lot of time in the industry is being invested in. It's something that really helps us address a class of quality regression that is otherwise very difficult to regress in terms of performance. And it's going to become table stakes soon enough. So I hope I made it sound exciting. I think it really is, and it's worth keeping an eye on. And that's kind of all I've got. I've got kind of a few high-level takeaways. I think quality is something you have to tend to over time. I think this is kind of obvious. We do a big design up the front. It's great. Everyone high-fives each other. We need to do things downstream of that I've talked about to try and keep things on the rails, to make sure that we don't accidentally lower the quality where we could have otherwise avoided it seemingly simply. Static and dynamic analysis, they have a lot to say about this. I certainly haven't talked about all the different things you can do here, but I hope I've provided a reasonable foundations. And I think encoding structural checks with things like architectural testing, with things like elaborate code QL queries, can really add a lot of value as well, if you've not played around with that before. And that's all I got. Thank you for your time. Enjoy the rest of the sessions.